So we're going to take a look at another projectile motion question here. This time the question reads, in a projectile motion experiment, a student measured the launch angle to be theta equals 45 degrees plus minus 1 degree and the range to be 15.5 plus minus 0.1 meters. Calculate the initial velocity and its uncertainty. So essentially all we need to do in this case is find the initial velocity, and then we need to see how the initial velocity could have possibly varied based on our calculations. So this is a little bit of an unusual question because we're given not much information. We're given a launch angle and we're given a range, and both of those have plus minuses on them. So we know we have to be clever here. We have to use a few different formulas. We know that x max, this is the range in x, is equal to the initial velocity in x multiplied by the time of flight. So this already we have some values for. We have a value for x max, we have a minimum and a maximum. We know that the time of flight is equal to the initial velocity in y divided by 4.9. So this is something that gives us the initial velocity as a function of time of flight, or time of flight as a function of the initial velocity. And we can combine these two formulas. So we'll call this formula 1, we'll call this formula 2. We are going to plug in uy on 4.9 where the time of flight is. So this gives us x max is equal to the initial velocity in x multiplied by the initial velocity in y divided by 4.9. Now, because theta is 45 degrees, this gives us a very specific relationship between u of x and u of y. And remember, we're not going to consider any of the uncertainties yet. We're just going to try and calculate the initial velocity. We assume these are equal. U of x is equal to u of y. This is the case where theta is 45. So this is our base case. So this means we actually have x max is equal to u of x squared on 4.9. This implies that u of x is equal to the square root of 4.9 times x max, which is 15.5. So we're going to calculate this. Square root 4.9 times 15.5 gives me 8.7149 ... This is the initial velocity in x. We know that the initial velocity is going to be the square root of the sum of squares of the two initial velocities. Given that these are both the same, this will be the square root of 8.7149 ... squared multiplied by 2. And so with our calculator we can use the stored value here. So we have the square root of the value we just calculated squared multiplied by 2. So we have square root of 2 times 8.7149, and that needs to be squared. That is 12.3247. ... So therefore, in this case, the initial velocity, which we'll call u, is actually equal to 12.32 to 2 decimal places. And that is in meters per second. So that's what the question had us do first. It told us to calculate the initial velocity. Now we have a slightly more difficult part. Now we have to deal with the fact that this initial velocity has some uncertainty associated with it. If we think about the theta angle, If the theta angle was higher, so if it was 46 degrees or if it was 44 degrees, these are obviously not to scale, this will affect the range. The 46 will have the object travelling not quite as far. The 44 will have the object travelling slightly further. This is our expectation of what's going to happen to the object. So this 46 or 44, the change in the launch angle, could cause us some problems here. And it could affect the range either way. So now what we need to do, based on the fact that this is our expected initial velocity, we now need to calculate what the initial velocities in x and y would be in the case where the launch angle was 46, in the case where the launch angle was 44, and see how those launch angles affect the total distance traveled. This seems like a lot of work in order to get this, and it is quite a lot of work, right? It is a lot of work to get this, but this is the question we've been asked, right? We've been given scarce amounts of information, not much information, and we've been told to calculate quite a lot about this particular scenario. So we've found this. So let's imagine we have the 46 degree launch angle. So this is 46, this is case 1. We have 12.32 as our vector here. We have a u of x, we have a u of y. So we can use sine and cosine to find the u of x and the u of y. Now I'm just going to do these quickly. So we have u of y will be sine, so 12.32 times sine of 46 will give me 8.86. 6 ... And then 12.32 times cosine of 46 will give me 8.56. Or 8.55 ... So this one rounds to 8.86. We're just rounding here because it's fine. It's going to give us a pretty good estimation of the error whether we round or not. And this one becomes 8.56. So now we have the u in x, we have the u in y. Now we need to use these to find the total distance that the projectile will travel. Well, we know that the time of flight is equal to the initial velocity in y divided by 4.9. So the time of flight in this case is 8.86. 8.86 divided by 4.9. This is 1.81 to 2 decimal places. And we know that the x max is equal to the initial velocity in x multiplied by the time of flight. So we know this. The initial velocity in x is 8.56, so 8.56 multiplied by 1.81, that gives me 15.4936. 15.4936 ... So the distance the object will travel in the case where the launch angle was 46 degrees is 15.4936 meters. So this is within the range they've given us here. This is greater than 15.5 minus 0.1, which is the lower bound. Now we need to do another case, case 2. Case 2 is going to be where the launch angle is 44. So we're obviously drawing these in quite an extreme way, but that's fine, it demonstrates the point. So we know this is 12.32. This is u of x, this is u of y. We can calculate both of these using sine and cosine. So we have 12.32 times sine of 44. This gives me 8.56. 8.56 to 2 decimal places. And then u of x is going to be 8.86. These are essentially just swapped around 2 decimal places. Now, we know that the time of flight is equal to the initial velocity in y divided by 4.9. So this is going to be equal to 8.56 divided by 4.9. This gives me 1.7469, so 1.75 to 2 decimal places. Now, as we did before, we know that x max is equal to the initial velocity in x multiplied by the time of flight. We know the initial velocity in x, this is 8.86. We know the time of flight, this is 1.75. And this gives us 15.505 ... And this is again within the range that we were given. Now, in order to do this properly, we need to work out which one of these is further from 15.5. From the look of it, it's going to be the first one. This is 15.5 minus 0.064. And so therefore, the x max from our empirical calculations, from actually putting these numbers in and calculating them, is going to be 15.5 plus minus 0.064. And these are the uncertainties that we've come to in this question, and these are the correct uncertainties that we want. Notice, in the question it actually told us it was 15.5 plus minus 0.1. That's pretty much correct, right? We've done some rounding along the way here. We haven't used any kind of complicated calculus to actually find perfect values. So what we're doing here is just plugging in numbers. It's just algebra-based physics, right? Algebra-based physics is not very precise. You're never going to get perfect precision. We've just done a bunch of calculations here to try and work out, actually, is 0.1 an acceptable range of possibilities, extremas? And the answer is yes, right? That's perfectly good. We got 0.064, 0.1 is fine. And most of the time when you're doing this, this is not professional physics, right? This is school level physics, introductory physics. You don't need atomic levels of precision in order to calculate things. You are just finding approximations. So if your teacher says, oh, you know, that's off by 0.0001, who cares, right? This is not the place for that level of precision. If you work in a, hadron collider or some kind of particle physics or medical physics laboratory, sure, you might need to be precise to a certain level. That's different. Right? That will require different tools, different skills. Here we're just using the information we've been given to calculate approximations, and that's what we did in this example.